Hello, hello. Hello, hello. All right, hang on, I'm catching up. Hold on a second. Okay. Yes, well said. Right. Yes. Yes. Hello, Maisha. Good afternoon, Athea. Oh, best. Wow. Okay. Hi, Alona. Good afternoon, Andrew. Good afternoon, Zemin. Oh, wait, more people could. Good afternoon, Zeman. Hello, Ruby and everyone. Hello, John. Hi, Michaela. Good afternoon, Eric. Hello, Nicholas. Good afternoon, Mark and everyone. Hello, Catherine. Good afternoon, Wee She. Hey, Rachel, and good afternoon, Rachel. Good afternoon, Jalen. Good afternoon, Manoj. Hi. Okay, that's funny. Hi, my, right, okay. Good afternoon, Catherine with a K. Good afternoon, Starnisha. Wait, oh, yes, I'm sorry. Yes, good afternoon, Starnisha. Good afternoon, Jessica. Hi. That is funny. Okay. Good afternoon, Elizabeth. Good afternoon, Alyssa. Hi. All right, I'm going to stay out of this whole, but okay, apparently you guys are friends, which is great. Wow. I'm okay. Oh my God. Okay, I don't want to hide. Okay, this is funny. Okay, hi, Rachel. Okay, hello. I'm sure you guys are too funny. Also, hello. If I missed anybody, I'm sorry. Did I say Manoj? Hello. Did I say Eric? Hello. But also let me. Oh my God. Don't tell me that you went to Carmine's on the Upper West Side. These sound like Italian. The buckets of penny. Oh my God. You didn't go to Carmine's. You did? Wait, you're literally talking about Carmine's? Are you serious? Oh my God. Wait, that's kind of cool that I just guessed that, isn't it? I mean, that is, oh my God. I do love that place. That's good. They had a scandal there. Yeah, that's really weird. I promise I just guessed that. Okay, that's weird. I do love that place. I mean, I haven't been there in years and years and years, but apparently, oh my God. Okay. But there was a weird story about that place. Wait, yeah. I'll take you there on a field trip. I'll drive in there from Maine. Yeah. No, I could see why someone should be excited to go to Carmine's. That place rocks. I mean, my wife is Italian, and even yeah, they had a weird story about recently. There was like, and I don't know if this is a coincidence. It has anything to do with why you're there, but there was a moment like a week ago where some people from out of town. This is a big deal. I mean, it's not a big deal, but it's a serious thing, actually. People were out of town and they were like waiting, online outside or whatever. And the hostess came out and just sort of was casually saying to them, like, okay, so we're going to be able to seat you next. And, oh, but you're not wearing any masks here. Please, we ask that when you come in, you have masks, or here are masks if you need them. And then apparently the people like freaked out on the host. I shouldn't say freaked out, that's it. But apparently they reacted quite, I don't know if anybody else has heard the story and can fill it in with more accuracy, but I don't know if it got violent, but I think it got very temperamental and very feisty. Like the people from out of town didn't just refuse to wear masks, but like went bananas on the host. And so, I mean, has anybody else heard this? Wait, let me see here. Yeah. Oh, so it was violent. So someone got a concussion. Okay. Yeah. Like that is, and maybe that's why it was on my mind when you mentioned Penny Olive. Okay. That's weird. Anyway. Yes. Well, yes. Good point. I agree with you. I mean, right. Okay. Anyway, but great restaurant. I totally agree. Okay. 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 Oh yeah. I mean, well, all right, let's not even go there, but I mean, yeah. Looking at the chat. Yes, insanity, right. And no, that's not, I don't mean that as any kind of critique of the restaurant. I think the restaurant is fantastic. I mean, it's been a long time since I've been there, but all right, anyway, okay, what do we have here? So I'm still behind, but I'm not going to talk about that. We're just going to do, one thing I do have to be clear, if there's anybody in the room, this is right now, just to be clear, this is physics 203, right? If you, physics 102 meets at 4:20 today or 4:30 today. If you happen to be in the room now thinking it's physics 102, then my deep apologies. I sent many announcements. If you're here for physics 102, then no harm, no foul, and I apologize, and I forget, but you can leave. If you're here for 102, come back at 4:30 p.m. I don't think that applies to anybody, but this is physics 203. It is not physics 102. My life is confusing. So if you're here for physics 102, you're not crazy, but please come back at 4:30. How is everyone's day? Okay. But let's, without further ado, we're just going to get back to, it was good. Oh my God, you guys are so funny. All right, we're going to go back. We're going back to, so we're going to finish. Oh my God. Imagine work being fine. Hey, now, wait a minute. Wait, I'm sleepy too. But wait, I'm going to have to respond to this. I'm going to move on here, but I'm going to respond to somebody in the chat here. Look at this. Yeah, John's imagine work being fine. I just want to tell you this. If you're a physics professor, if you choose to spend your life teaching a subject that you love, then work is almost always fine, yo. I mean, let me tell you, I mean, maybe not always in COVID, but if you have the job of your dreams, then work is, and if you're honored to teach at an institution like John Jay with students like you people, then work is always fine, comma, yo. Okay, motivation. All right. I mean, maybe I'm slightly exaggerating too, but okay. All right. So we're going to go back. It's time for us to finally freaking fit. No, that's good. Yeah. Like, wait, what did John? No, that is, yeah, and let me, and it is really true, and yeah, we could talk about that at some point too. Yeah, okay. I told you. Okay, we are going to finally finish. All right, I've got to start ignoring the chat. This chat wreaks havoc on my ADHD and my self-esteem. Okay. Yes, well, thank you, Rachel. Oh, that is totally, I actually think that I knew that, but I totally appreciate it, Rachel. That's a very polite way of getting us on track. Yes, so we are, yes, on the very last problem of homework 1. So here we are, boom, boom. Okay, right, yeah, I kind of love that Rachel knows that too. Yes, let's go. Oh, wait, is that Let's Go a Mario reference? All right, okay. I'm really gonna shut up. Either that's a reference to Carmine's or to Mario. And I want to say okay, I'm gonna say yes, awesome. I'm gonna say this now just because I'm stalling because you guys make me so happy. So I have a 7-year-old son, right, and a 17-year-old son. My 7-year-old son just had a birthday, and we, among other things, we got him like a fish tank, whatever. And there was going to be like 2 fish that we're going to put in the fish tank. And my 7-year-old son turns to his grandma, my 75-year-old mom. Okay, this is a story about, we'll talk about inspiration. The 7-year-old turns to his 75-year-old grandma, completely out of context, and says like, grandma, if we get 2 fish next week, like, what do you think we should name the 2 fish? And grandma does not skip a beat, looks at the kid, looks at my kid, and says, name the 2 fish Mario and Luigi. I mean, is that not like, how hip and cool of a grandma is that? Like, I was like, I was like, Mom, you have done your homework on this planet. Like, wow. Thank you. Yes, I'm going to tell her that you all said that. Okay. All right. So anyway, yes, we're on last question of, oh wait, someone's coming. Sorry. And yeah, it is cute. She is cute. All right, I'm totally, it's you on your laptop. Oh, no problem. Of course, if I ever called her Grandma Yavram, she'd be scandalized because that's my dad's name, and my mom is not married to my dad anymore. It hasn't been for long. But anyway, whatever. Okay. But yeah, she is a real one. She is a deeply spiritual woman. All right. All right, so we're on the last question of homework 1. We are actually going to move to homework 2 today, which is so exciting. Here, special guest. Oh, well, someday. She's not here right now. She'll be a special guest someday. Oh, I have stories about that too. Oh my God. Anyway, you guys stop it. Just stop it. All right. So here's notes on the all right. No, really, I'm going to turn my chat off. This is just, but you're, boy, oh boy. Yes, physics. Thank you, Rachel. See, she's the linear one here. All right, all right. Okay, I'm really okay. I'm literally okay. I'm turning my head. I'm turning to the okay. So the board. So question two. The question two is from t equals 3 to t equals 7. What is the average velocity? Right. So I wrote the question. I probably should have said C diagram above. So we have our diagram. There's the question. So that's steps 1 and 2. Then step 3, notice GDP. I write down the definition of average velocity first, right? The definition of average, and it's the only equation we have right now. But the definition of average velocity is displacement per time, or in other words, change in position per time, right? And so now I'm going to step 4, which is, PAW, particular application and work. So in other words, in effect, I'm plugging in the numbers and watching the units. Oh my God. Okay. I'm so not looking. I'm not looking. But I will in a minute. So, the t equals 4 because we're going, the time is 4 seconds because we're going from t equals 3 to t equals 7. I'm just sort of reading what's on the board here. Stop me if it's unclear. But then I need to know the 2 positions. Now, notice just one little, oh my God. Okay. I'm so not, I don't even know what you're talking about. I'm not looking. So I have to put in what x naught is, and I have to put in what x is. Just please do notice this one time. I think you're all clear on this. I'm not going to dwell on this question forever or whatever, but just notice x naught, x sub 0 is supposed to mean, the very first position, the initial position, the position when you start your stopwatch. But just please do note, now that we're getting used to this, when you start your stopwatch means when you start paying attention. It does, like t equals 0, again, what I'm trying to say here is t equals 0 does not mean the Big Bang, nor does it mean the Garden of Eden, right? T equals 0 does not mean the beginning of all time. It means the beginning of a given experiment. And an experiment really means, the beginning of an experiment really means the beginning moment when you start collecting data, when you, the researcher, starts paying attention, turns on his or her stopwatch, right? And that, to be very clear, that could mean even in the middle of something else that somebody else considers to be an entire experiment. In other words, here, x naught is not where the instructor was for the beginning of this whole homework sheet. It's not x equals 4. It's where we start beginning to pay attention for this final segment from t equals 3 to t equals 7. So x naught here refers to the position when t equals 3, right? Like the beginning of this segment that I'm paying attention to. I mean, the technicality, but it's just reinforcing the idea that the 0 moment in time and the 0 coordinate of space are always up to us. We choose our coordinate system, and we might re-choose it for each new situation that faces us. All right, anyway, but I think you get that. So the initial position is -2, because that's where the instructor is at t equals 4. And then the final position, the position where the instructor is at t equals 7, is also -2. How do I know that? I mean, I wasn't told in the fact pattern of the problem or anything. There's no picture of that, but I just figured it out in some prior question, in question 1 of part 3. So we use that information. So bottom line, from in these last 4 seconds that we're looking at, the instructor went from a position -2 back to a position -2. Ultimately, the instructor was not displaced at all. The initial position and the final position were the same. So the final answer to this question into the whole sheet. The whole sheet is that the average velocity for that last segment that we're looking at, or this particular segment that we're looking at, the average velocity is 0 feet per second. That is always true for any round trip. Anytime you end up where you start, you have been displaced, not at all. So your average velocity is 0. Your average speed was something else. His average speed was not 0, but we're not being asked that here. We're being asked the average velocity is 0. So that's it. That's the answer to that question. I'm almost going to take the risk of looking at the chat in a couple of moments, but first I want to say, since we're finally about to move off this sheet, thank God, and move to the next sheet. I mean, assuming there's no questions, like I'm gonna pause for a second and look at the chat just to make sure there's no questions at all about this homework 1. Oh, again, I still have to return it to many of you, or I have to return revisions to some of you. You can still turn it in. Like, we're putting it to bed in terms of talking about it in class. I'm now going to feel that you have all the answers and all the solutions if you ever want to look at it again to study for an exam or something like that. But you still can turn it in, or you can turn in revisions and just consult, whatever we did in class in order to do that. It is still fair game academically, but intellectually, I think we're done. The summary of findings from the sheet 1, like, since we've spent this much time on it, let me just make sure we get what are the takeaways from homework 1. First of all, we have 4 types of measurements or quantities that we introduced for the class. At this point, we have 2 scalar quantities. Scalar quantities means quantities that are just concerned with magnitude or size, right? So we have 2 scalar quantities that were introduced in the sheet: distance and average speed. We have 2 vector quantities that were introduced in the sheet. Vector quantity is a quantity with both magnitude and direction, right? So the 2 vector quantities that were introduced here are displacement and average velocity. So in other words, ultimately, distance is like the magnitude of displacement. Average speed is like the magnitude of average velocity. For most of this class and for Physics 204, we're going to be more frequently than not concerned with vector quantities. So most of our equations and symbolisms that we're going to start developing are going to be based on those kind of quantities. We have 1 equation thus far with all of our work that we're doing, or all of our yapping. We have 1 equation in this class so far. Obviously, we're going to get more, but we have 1 equation so far. It is merely, and it's a triple equal sign equation. It is the definition of average velocity, our only equation so far. So I want you to just bear that in mind, that the only equation we have so far is simply a symbolic abbreviation or expression for something that I'm hoping you see at this point makes sense in English. It's just an English statement that average velocity is defined to be the total displacement you undergo in a total amount of time. It's just a definition, which means that if it's ever right, it's always right. It was not discovered in the lab, therefore it's never going to be, it was not proven in the lab, therefore it's never going to be disproven in any lab, right? It's not subject to technology overturning it. That equation, V bar triple equal sign x minus x naught over t, our only equation so far. If it is ever true, if it ever makes any sense to you, then it's always true because it's a definition, right? So that's the findings from this sheet. I'm about to now move to sheet 2. Here's sheet 2. Okay, we're coming. Average speed. The sheet begins with 3 warm-ups. They're meant to just be practice exercises in the definition of average speed. Since they're practice, and since I want to start making tracks now, speeding up a little bit now, what I've done here, just notice, and I'm going to stop. I'm going to look in the chat for a second. I just want to put this sheet up so you can see it. Notice that what I've put here is the 3 answers for the warm-ups. Like I would not accept, this is not a complete example of how you're supposed to do homework for me, right? Like, you are supposed to show the diagram. You are supposed to, show what the question is. You are supposed to write a general definition or principle, blah, blah. But here, in order to sort of move things along, I'm just putting the answers down so you can check if your answers are right and make sure you don't have any questions or issues. So those are the 3 answers for the 3 warm-ups on homework sheet number 2, average speed. I'm going to pause while you just look at this or see if you have any questions. And I'm going to see if there's any questions in the chat, but I'm afraid to look at the chat because I know I'm going to laugh. Okay. Look. Oh my God. You guys are too far. I'm going to miss this class after I kill you all. No, I'm going to miss this class. I didn't say that. That's totally inappropriate. I'm going to miss this class for real, but I'm going to see you all again in another semester after you pass this class. All right. So I'm reading the chat. There's like funny emoticons, blah, blah, blah. Okay, Nicholas, that is funny. Whoa. Okay, Althea. God, if I wrote average velocity out the way Althea did, it would take me like 4 years and 3 keyboards. Okay. Don't be tempted. Yeah. Oh my God. Whoa, those are some serious. I don't even know how Althea did those symbols. Okay, I did. Oh my God. You guys are too funny. And I don't really mean that. You're not too funny. You're exactly the right. Oh, wait. Oh, okay. Oh. Wait, okay, I'm still looking at the chat. Hand empty, no thoughts. Wait, wait. Oh, there's a lot of chat. Okay, welcome back to the chat. That's hilarious. For 2, I put okay, wait. So now John's, okay, good point. So, and again, I'm just putting the answers here, not to discourage questions, but to kind of get to the questions faster. Like you don't need, I'm electing to not drag out all my work on there, but yes, good question. Like, for example, from John Ford, like wait, for 2, you put 0.417 yards for today. That's interesting. If you put 0.417 yards per day, is that because you somehow, I'm not sure how you got that. Is that because you subtracted out the zeros or so? Like, I think what I'm trying to say to everybody is, or the purpose of question 2 is just to reinforce that even if there's moments where, even if there's 3 breakdowns, even if there's times when the car is not going at all, 0 is a number like any other numbers. The definition of average speed is just the total amount, how far you got, divided by the total amount of time you took. So even if sometimes you weren't going anywhere, that just still counts in the average. So I'm not sure. 0.417. Did I do something wrong? Let me just look at the. Well, so I'm going to go back to John. Wait. Oh. Wait. All right. Maybe I should read the whole chat before. Please ask you. Yes. How did you even get that? Wait. Did we do number 2? Oh, well, number 2 of part 3, I think is. Okay, wait. I'm going to go teach us your ways of the. All right, hold on. I guess I'm leading. I'm going to read all the questions and decide which to answer in what order. My issue in physics. No. Physics with a side of comedy. Okay, that's funny, but wait. At Rachel, oh my God. I do think we did here, as far, I'm jumping around here, but as far as question 2 of part 3, but, and I think if anybody deserves to be sure that she's clear, and I think it's Rachel for sure. But yeah, I think this was question 2 of part 3. Like, I started it right here on this page. I'll let you look, and then it goes to the next page. Okay, wait. So there is a lot in the chat. 4 times 24. Wait a minute. Oh. Okay. Okay, wait. So there are some good questions here. I hope I don't skip. So first of all, yeah, I mean, I think as far as part 3, question 2, it's here on the screen, and then this. I can go back, and I don't mean this sarcastically, like to Rachel or anybody else. If you missed, okay, I think the answer to question 2 of part 3 of homework 1 is 0. All right, now this is getting crazy. Is 0. Like, basically the just. Oh, okay, cool. Thank you. Okay. Now. Oh, I see what John's saying. I'm sorry. Okay, I'm so stupid. I didn't say that. It was a stupid that yes, you do support each other. No, that's very nice. On John's question, I see what's going on. Right. So John, he's not wrong, but I see what's happening now. So John decided to convert. Thank you. Thank you. Uh, what John did for part B. So now I'm on homework 2, everybody, right? I'm on homework 2, joke 7. No, I'm on homework 2. Oh my God. All right. Thea's got to stop it with the fonts. Like, well, like, unless she's willing to put this on a T. Yes, homework 2, joke 7. Okay. Oh my God, guys. You have to remember too. No, you don't. Look, when I was, whatever I have, like, now we all call it ADHD. When I was young, they didn't call it ADHD. They just called it genius. You know what I'm saying? No. All right. Wait. You have a comedy club. Wow. All right. Well, when they try to get off the topic and stall, do they just like do random physics equations? Like what? Okay. Okay. Wait. John Ford did a legitimate thing. I do want to address the John Ford thing here. What he did in question 2, he's not wrong. It's just that he converted his answer, or he converted the work or the information or his answer into yards per hour. I missed that. I didn't catch that. And it made it more complicated. He had to do more work to do that. And he got a more complicated answer. There's nothing wrong with that. But what I do want to stress is it wasn't necessary. In fact, part of the purpose of these warm-ups is to actually show the units for speed, for average speed, are distance units over time units. Now, yes, there's a lot of advantage to MKS units, to SI units, whatever, to metric units. There's a lot of advantages to that, but there are also advantages to other units as well. And SI units might be often preferred in a science class or preferred in certain contexts, but that's just it. They're just preferred. They are not objectively more correct than in the other units. And the whole purpose of choosing units is to choose something convenient. You're going to see in the, right. Okay. Like we're actually going to see in the next part, like convenience is a big deal in physics. Like truth of the matter is, like nature is already complex. Nature is already a mess. I shouldn't say that. Some of my best friends live in nature, but like, including me, nature is already complex. We're not here to be nature. We're here to study nature and call it physics. And to study it means to try to extract some kind of organization or some kind of simplicity out of nature and be able to hold it in our minds. Like our job is to make what we see somewhat easier and more accessible to us. I don't just mean as teachers and students. I mean as scientists, right? Nature doesn't need our help making things any more complex. What we're trying to do is make it simple and i.e. convenient for us to be able to navigate. So convenience is like a very important standard in science, believe it or not. And so what I want to say here is the units are like significant figures. The units that you want to present your answer in should first and foremost be whatever units the question's presented in. If you make measurements in a lab in certain units, then you present your finding in those units. We do need to know how to convert back and forth for a variety of convenience-based reasons, but you don't have to convert just for the sake of it. I mean, and to put it one final way, like, sure, sometimes you might think if I give you yards, you might think, oh, he really wants meters because he's a scientist. Well, maybe not. But that wasn't even what's happening here. I mean, I gave you in yards and day. The truth of the matter is to convert to yards per hour might have some kind of benefit somehow, but it's a little bit arbitrary because there's nothing more proper about yards per hour than yards per day or yards per second. I mean, like, if anything, you would want to convert to meters per second, I suppose, if you want like Professor Sheehan's stamp of approval or something. But anyway, what I'm saying is what John Ford did is not wrong. It's not wrong. It's just unnecessary. Okay. Right. That's basically what I'm saying. Okay. Right. So yes. Okay. So John, your answer is still good. Yes. It's just, it's not, it's fine. And if you did it on a test, on an exam, would I give you full credit? Yes. But would you possibly be giving yourself extra stress and a little bit of extra time on the exam that wouldn't necessarily be ultimately productive for you? Yes. Like it's not necessary. But yes, it's still good. You'd get full credit. Okay. Still amazing. Oh, yeah. So what I want to say to everybody is when in doubt, the units that I want your answers in are whatever units the question's presented in. If I don't specifically, I mean, and that is like a science thing, or like just like whatever number of significant digits I present the numbers with, then leave your answer to that level of significant digits. I mean, it's a fair question. It's a fair point, and that's my answer. All right. So I think the most cool. Thank you. And I appreciate it. And that's totally points for closing a conversation. Thank you. All right. Did I mention I love this class? I love this class. So yes. Yeah. Oh, good. Why don't you just point out when the man makes a tile? That's good. Like he isn't already. God. Okay. I thought you support each other, people. I thought you support each other. And then she's like, all right. Anyway. So yeah. Okay. So average speed 30 miles per hour. Average speed for the second one, 10 yards per day. Just notice the zeros don't change that number at all. And then, okay, for the final one, someone asked me a question. Someone in the chat asked about that final answer. Now I did put my answer in scientific notation. You don't. Oh my God. Okay. Good point. Fair point. But for the final answer, I wrote in scientific notation because like this is like otherwise I would have a million zeros in my answer. Scientific notation, again, it's not required. I just think it makes it more convenient. If I have a bajillion zeros, I want a more straightforward, simpler way of writing the number. But if you, in other words, I guess, but if you wrote for your final answer for C, if you wrote, sorry, if, I just don't want to flip the page because there's more going on the next page. If for the final answer you wrote this would be correct. That's totally correct. If you put that on an exam, I would give full credit. 186 million miles. That's the answer. But one person I think asked, like, I noticed that the answer to question C is kind of like a little bit like question 1 of part 3 of what we did on Monday. That is, by question 3, I'm giving you an average speed and I'm giving you a time and I'm asking you for a distance, right? So in effect, I am asking you to take one step of thought and rearrange the equation, right? Like I'm giving you, I mean, you're in a way doing distance equals rate times time here, right? Oh, okay. You see what I'm, okay. I thought you were at work, whatever. Or is that somebody else? I thought she's like talking about multitasking. I can't even single task. I don't know if you've noticed. But yeah, so question C is asking for a distance. Therefore, the units, that you get for your final answer should be distance units like miles. And the way you get it is you multiply the speed times the time. Again, just to reinforce, I don't think that's a new formula or a new equation. And I don't think it's like unfair or something. I'm just saying, given that this one equation, this definition of average speed, you should be able to rearrange it in any way you want. In fact, foreshadow to the next problem we're about to go to. If you understand that average speed equals distance over time, then yes, I expect you to also be able to understand or reproduce that distance equals average speed times time. But also, here's the hardest one. You could also cross multiply twice or whatever and recognize that distance equals, sorry, that's not what I mean to say. I mean, you should also be able to see that time equals distance divided by average speed, right? Like it goes in any direction you want. And that last one comes up the most uncommonly, the most infrequently, but it's still true. Distance equal, I did it again, time equals distance divided by average speed, right? And if you look, the units do work out perfectly, blah, blah, blah. All right, so, right, exactly, Ruby. So yeah, so I'm saying the answer to this last one to C, it's 186,000 miles per second times 1,000 seconds. So it's 186,000 times 1,000. I'm sorry. Yeah. So it's 100. Right. Okay. Cool. Right. So, and 1,000 times 1,000 is 1,000,000. But yeah. And cool. Thank you. That counts as closing a conversation too. By the way, for perspective on it, so those are just supposed to be warm-ups. They're not supposed to be a big deal. I'm not saying they're easy. I'm just saying, okay, hopefully we're on the same page here with those warm-ups. But by the way, that is accurate information about the speed of light, just for perspective for a minute. So this is not a joke, what I'm about to say. It's not something you're responsible for just for perspective. Like the speed of light is, and the speed of light becomes like our big focus by the end of physics 204 is sort of the, okay, I'm going to look at that in a minute, maybe. But in the metric system, the speed of light is 3 times 10 to the 8th meters per second, 300 million meters per second. You may see that a lot in science books and stuff like that, but we tend to think in terms of miles and stuff as American human beings. So for perspective, it is like, if you do the unit conversion, the speed of light is 186,000 miles per second. Now that's just to tell you how fast that is. I mean, that is fast. And that's an accurate number. This is how fast that is. The entire circumference of the Earth is like 24,000 miles, okay? I'm not saying you have to memorize that. I'm just saying it's true. It's kind of easy to remember though, because like 24 hours in a day, 24. Is that, oh my God. All right, I'm going to totally look at that in a second. Oh my God, stop with the chat. Or don't, I'm not sure. But the whole Earth is 24,000 miles around. That means if you unwrap this, like light does not travel in curves, but just imagine like unwrapping the circumference of the Earth and making it a straight line. It would take the equivalent of almost, I will. Oh my God. What I'm trying to say is that in 1 second, light goes the equivalent of almost 8 Earth circumferences. Like that's how, like literally, like a picture, the equator of the Earth, unwrap it, make it a line. 8 of those equators unwrap is how fast light goes in 1 second, i.e., like no matter where you would stand on Earth, the farthest away anybody could be from you on Earth, like the farthest anybody could be from you is 12,000 miles, right? Because like if they went all the way around, they'd be back standing next to you. So the farthest away anybody could be on the Earth from anybody is 12,000 miles. That means that that to shine light anywhere on Earth to anywhere else, it's going to take less than a 16th of a second for light to get anywhere on Earth to anywhere else, less than a 16th of a second, anywhere on Earth to anywhere else on Earth. If you shine the light, if you could make a light go that far, or anything that travels at the speed of light, like instant messaging or like chats, takes less than a 16th of a second to get from anywhere to anywhere on Earth. So I'm bringing that up to just say a 16th of a second, right? Like that's less than a snap of the fingers. That's such a small interval of time that we didn't even have clocks that could even measure or even pick up that small interval of time until like the 20th century. So it's not shocking or weird that for most of history, most thinking, writing, experimenting, observing people assumed that light just got from one place to another in no time at all. Like most scientists, if you want to say, or like scholars for almost all of history regarded light the same way we all did when we were children, which we just figured light just gets there in no time at all, i.e. we just figured that light had infinite speed. That's what it seems like on Earth, that light travels at infinite speeds. It turns out it's a very major breakthrough that light actually does travel at a finite speed at all. Like it's really fast, but it's still a finite number. It actually takes time for light to get from one place to another. Let me push that point even further just for perspective. I mean, I know you all know this, but like actually think about it for a minute. Like it really is, even though this is a cliche, it's totally scientifically absolutely true that it takes time for light to get from stars to our eyes, right? The farther away a star is, the longer it takes for light to get to our eyes. Typical stars, like the very closest star, literally, this is true. The star in the sky that is closest to Earth, other than the sun, I mean, the sun is a star, but other than the sun, the star in the sky that is closest to the Earth is almost 4 light years away, i.e. it's so far away that it takes light 4 years to get from the closest star to us. And that close star, by the way, is called Alpha Centauri. You can't even see it in the Northern Hemisphere. You can only see it from like Australia and New Zealand, blah, blah, blah. Typical stars typical stars that you see from the Northern Hemisphere or New York or whatever, I mean, with your naked eye, a typical star that you would see just like randomly, like, you know, Orion's belt or something, is at least 400 light years away. I just consider that for a minute, meaning that anytime you look up in the sky and see anything that's actually a star, like not a planet or not the sun, but anything that's a star, and you're like, oh, that's a beautiful star. Like, please understand that when you say, oh, that's beautiful, you don't actually mean that's beautiful right now. You mean that thing was beautiful 400 years ago. Like, it is a cliche, but it is not science fiction. It is science that when you look at a star and you're like, wow, look at that. That looks so cool. No, what you're seeing is what it looked like at least 400 years ago, if not 1,000 years ago. And does that mean that right now the star that you're seeing could actually have blown up 200 years ago and not be there at all right now? Yes, like absolutely. When you look at a star and you're like, that is great, what you really mean is that was great. You have no idea. We have no idea what's happening in that point in the sky right now. We won't know for another 200 or 400 or 1,000 years, depending on what star you're looking at. The farther out you're looking in space, the farther back you are looking in time. Definitely no joke, because light takes time to travel. Just that, now that's a sidebar message, but just to kind of keep everybody hooked into physics, like that is no joke. That's true. So this little warm-up exercise about the speed of light is just trying to, you know, like remind you that like just the notion of distance equals rate times time is, it has implications. It means the farther we look in distances, the more back in time we're looking. Like, kind of interesting. I'm going to look at the chat and I'm going to regret it, but then I'm going to move on to the next question on the sheet, which is actually a hard question. It's not meant to be a trick, but it is tricky. So I'm going to be serious about it when I, oh my God. And of course I'm going to run out of time. Oh no, I'm not actually. Okay. But I'm first going to look in the chat because I'm courageous. Oh my God, I'm going to, what do you call it? I'm going to dare gently or whatever. I'm going to like walk through the fear. I'm going to be like Brene Brown and Glennon Doyle. I'm going to like totally look at the chat. I'm going to marry a professional soccer player. Okay, blah, 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 blah. All right, hold on a second. Okay, Rachel, don't want, it's, oh my God, please look, oh my God. Oh, okay. Oh, okay. I can't believe this chat is going to be done. Ha! Okay. That's funny. The Nicholas thing is funny. It's particularly funny that I actually have mixed feelings about Neil deGrasse Tyson. I have to admit, I have some mixed feelings, but that's a good line. That is a good line. And if it came from him, okay. Nick, please, okay, best you. Okay. What if you were on a different floor? That's hilarious. Then your average velocity would be a little bit higher. Okay. Oh my God. I wish you put it. Okay. I'm crying. I thought it was dying. You're crying. All right. You're talking about dying. Right. Okay. Nick, I beg. Yes, you can include that. Nick can totally include that joke in his submission for turn 5. Please look. Oh my God. Yeah. Meanwhile, Maisha retired. She's, I don't know. Okay. It's not whatever. SMH. Wait, SMH. I don't know what's SMH. Okay. It's with Rachel. No one. I'm staying out of this now. All right. This chat is moving. That's funny. Okay. Stick with you. Whoa. I don't know, Rachel. I mean, Rachel, they're giving you a hard. I don't know, Rachel. I'm kind of, I got your back here, Rachel. Oh my God, Athia, what, dude? All right, I'm gonna. Whoa, she called you a.
Oh, I know where what. You can't do that in front of the design. How about we put that design at the front under the gun?
And also, what's
Is there a fire on the building or someone smoking?
Someone smoking. Actually, no, I think somebody trying to burn down the building because I heard.
Yeah, there was an alarm in the morning.
Yeah.
I was in the class, so it was like a false alarm.
Stop me asking. Yeah.
Oh, cool.
All right, I would like to do physics, but wait, everybody's okay. This is a joke about the far. Okay. I'm going to quickly see, and there's a problem. I do have to quickly scroll through the chat because there might have been legitimate physics questions in the chat. So I hate to. All right, so let me just. But yeah, and let's not call each other haters. I know, and in print, it's a little sketchy because what if someone screenshotted it and then they totally put it on Snap? Like, let's not call each other haters and you're a bully. Like, really, this. I mean, okay. But I said that. Okay. And I know we're joking. I do love this class, but we do have to be careful about Facebook. Oh my God, I still have to. Okay. Redemption arc. Wow, that's a phrase. I didn't even know that phrase. Wow. Okay. No thoughts. Okay. Stars are definitely hipsters. Yeah, you're seeing stars. Yeah, no, you're seeing. Yeah, yes, you are. That's right. I'm starting. Okay. Okay. Ooh, all right. Good question, Althea. Okay, I like it. I'm going to ignore it. But physics. Okay, physics. Okay, I'm moving on. I'm waiting to. I got the. I need it. Oh my god. Oh my god. Okay. Yes, HillFigure. Thank you, Starnisha. And yes, and we totally have to go over HillFigure. That is the point of today. And yes, okay, we're doing physics. And I apologize if I'm all right. Okay. HillFigure. Now this is, it is true. I'm looking at the time. I am really going to try to be serious now for, we have like 30 minutes left. HillFigure. Okay. In all seriousness, I am going to, and HillFigure is not a joke of a problem. Okay. But it's a very important illustrative physics problem because it's not a trick. Some of you might even feel by the end of it that it's like unfair or something like that. And I sympathize with that, but I don't think it is unfair. I think it's very representative of a feeling that we can have in physics often where it can momentarily feel unfair. But like, so can a thunderstorm. I mean, no joke, like it's maybe physics is occasionally unfair, but only as unfair as nature is. And I don't really think nature is unfair. I just think nature can be harsh and temperamental or whatever. What am I getting at? I'm getting at this. This is a seemingly simple problem. It is simple. And it's a problem. It's asking us about average speed, a concept that we've been talking about here. And ultimately, I'm going to show you that the only knowledge you need to do this problem is the knowledge that we have, which is the definition of average speed, or if you even like the equation, we'll even write an equation form, like, like average velocity is displacement per time. And what is average speed? It's like the absolute velocity of average velocity. So okay. So yeah, the equation would be that equation that we used a second ago, like V bar equals X minus X naught over T. And I'm going to do it in a second, but I want to warn everybody. And, some of you might have gotten the right answer to this. Some of you might not. It's not asking for any information that we don't already have in this class. And also, it's not asking for us to do anything with that information that we haven't already done in prior problems. We're basically just going to use average speed equals distance over time and maybe rearrange it a couple of times if necessary, just like we've been rearranging here and there. But what we're going to find when we do that is we're going to get an answer that it might slightly surprise some of you. Like to cut to the chase, the answer to this question is not 50. Okay, in fact, oh yeah, I guess it says right there, the answer is not going to be 50. And we're going to prove that. We're going to see that the answer, we're going to see why the answer is not 50, and we're going to see why the answer is something else. And we're not going to do anything tricky in order to prove that. What we're going to do is avoid doing something tricky. Let me just remind you of the question. And again, I think this is maybe tricky, but it's not a trick. So what's the situation? The situation is we got this car that goes up a hill at 40 miles an hour on average, or constantly, either way, whatever. It goes. Okay. And I'm sort of trying to, oh, cool. Okay, cool. No, that's good to hear. We got a car that goes up a hill at 40 miles per hour, and then it doesn't waste any time turning around or anything like that. Like no tricks up our sleeve, no complexity. It just like quickly turns around and then comes down at 60 miles an hour. And what we're asking is, what's the average speed for this whole round trip? Now, the average velocity for the whole round trip is definitely 0 because it ends up where it started. But here we're asking what's the average speed for the round trip. So that's not 0. Like, in other words, it goes up at 40, it comes down at an average speed of 60, not negative 60, right? We're not dealing with velocities here, we're dealing with speeds. And so I'm just going to start doing the math in a second. But also, to be clear, like, we're saying that this is up and down a hill, frankly, just to make it sort of easy to picture and to make it realistic of like why we would have those two kind of numbers. Like, we might imagine someone's going slowly up a hill and coming sort of quickly down the hill. But to be clear, it doesn't have to be a hill. Like, the hill is not the trick of the problem. whatever answer we get is not because it's a hill. It could have just been something that goes there and then comes back. And in fact, let me go a step further, because someone did ask this in the other class. It doesn't even have to be a round trip for any of the logic we're about to do. It doesn't even actually matter that it's a round trip. That just makes it easier to picture and easier to contrast with velocity. But for all intents and purposes, this problem could be stated: an object goes a certain distance at 40 miles per hour and then goes that same distance again, but at 60 miles an hour. Like, it could be distance and then distance. It doesn't matter that the thing turns around, honestly. And it doesn't matter that it's a hill. That is just to make it easier to picture. Okay, so we want to know the average speed for the whole round trip. Now, if you put 50, I am saying that's wrong. I'm not saying that to shame anybody. I totally get why a lot of people would put 50. There's, of course, a very logical reason or reasonable reason why a lot of people would put 50. The reason they would put 50 is that presumably they're taking the two numbers 40 and 60 and averaging them in their heads or on paper, like they're adding 40 plus 60 and dividing by 2, like you're getting 100 divided by 2, or they're just picturing like the number that's right in the middle of 40 and 60. Now, that's not crazy. If you got 50, you're not crazy and you're not irresponsible and you're not immoral, but you are wrong. And here's why you're wrong: because we're asking for the average speed. And we have one and only one definition of average speed. What we know is that average speed always is defined to be is equal to total distance over total time. That is what average speed is. If you take these two numbers and you average them together, what you're thinking is, oh, average speed, I guess that's the average of the speeds. Now, that's not crazy, but we never said that. And I'm not trying to be a jerk, but this is a very important thing. If you just average those two numbers, what you just did was you made up a different idea. You're saying in your mind, I bet average speed should be the average of the speeds. Now, again, I don't think that's crazy. I don't want to stand here and tell you, no, why would you think that average has anything to do with average, you lunatic? Like, no, average does have something to do with average. And in fact, if we're really careful about this, we're going to find that a lot of times, if you're really, really careful. Okay, I'm sort of looking at chat. Wait, hold on. These are legitimate physics things in chat. So a little bit. So John's question is a good one. The answer is a little bit more detailed than that, so I'm getting to it. Now, 30 is a reasonable guess too, but 30 is a little bit odd because that's lower than either of the two numbers. So it would be a little bit odd if you went 40 for a while and you went 60 and somehow your average turned out to be 30. That would be a little, but here's what but bear with me. I'm going to explain this. I just want to say, if you got 50, it's because you averaged the two numbers together. And I'm not saying that that's always crazy. It might even be sometimes true. It might even sometimes work that the average speed for a certain interval has something to do with the average of speeds. But what we know for a fact that's always true is that average speed equals distance over time. That's the definition. That's why I always say step 1 is draw a diagram, blah, blah. Step two is like, what is the question? WIQ. But step 3 that we should always do before we start plugging in numbers, before we skip to showing customary work of plugging and chugging and looking at numbers, before you look at numbers and you plug them in and you manipulate units, you should always write down a general definition or principle first. Remember, always write something down that's true and then try to make it relevant. So what I've done here, so I'm saying what's true is that not quite. Okay, now Alona is getting closer and closer. We're going to end up seeing that the truth is somewhat closer to what Alona is saying here, that if you really want to average things, you're supposed to add up all the terms and divide by the number of terms. And it looks here, what people might do fast in their mind is think that there's two terms, 40 and 60, just add them up, divide by 2. Alona's onto something when she suggests maybe it's more than just 2 terms. That's what we're going to find, yeah. But what I'm saying right now is we'll find that out. Right now, that's pretty clever. What Ruby's saying is pretty clever. Yeah. Now, I actually do agree with what Ruby's saying, and that is pretty awesome. But I'm still going to explain it my way, partly because she's not wrong, she is right. But there may definitely be people in the class who, even if they see that Ruby happens to be right, they might be thinking to themselves, and I might even be one of these people like, all right, I guess I see why what Ruby's doing turns out to work, but I don't see why or why I would have ever thought of that. And I'm not trying to put Ruby on the spot. She's totally right, but but if you don't see just yet why you would ever think to do that or why she'd be right, then fine, bear with me, you'll see. But and plus notice that what people are putting in the chat are different interesting like math ideas of what you guys are sort of trying to do in the chat, and you are with me, and I'm not joking about this. What I see is that people are following me and sort of seeing that there's some kind of wrinkle here. So people are coming up with sort of cool math ways to see that the answer is not 50. But what I'm really trying to encourage everybody is hang on with the math, hold off on the math. Let's do physics. There's only one physics, like we're being asked about an average speed here. And we know one and only one thing about the physics idea of average speed, and it is total distance over total time. So if this were an exam right now, like even if whether we think we know the answer or not, like this is the habit I'm trying to get everybody into, whether you think you know where the whole problem is going to land or not, you do know how to begin problems. If we're asked for average speed, write down the definition of average speed. Average speed equals distance over time. Now specific, right? Like as I'm saying on the sheet here. Now specifically, average distance over time, we want for this whole thing, this entire round trip, we want the total. So specifically in this case, we want the total distance over the total time, right? I'm not making up a new formula. I'm not making up a new concept. I'm not making up new math. I'm just like before with the number line problem, notice that whenever we were evaluating some segment of the experiment, we decided what segment we were evaluating. We looked at one section at one point, we looked at a different section at another point, and another point, we looked at the whole thing. And we just to be consistent when we make these choices. So here, if I want the average speed for the whole thing, that means I want the total distance over the total time, which simply means I want the distance up plus the distance down all together in the numerator, all over the time up plus the time down, right? Like what I want everybody to see is notice what I've written by the time I get to the bottom of the sheet. Everything I've written now, I think you'll agree is true. It's like definitely true. It's definitely not new information. It's just an expansion of our general definition that we've had all along. It's definitely true. And if you were in an exam right now, you get a lot of points for writing all this. Like you've just done 3 steps of the problem and everything you're saying is true. I haven't plugged in one number yet, but everything I'm doing is true. And it's not only true, it's about to be helpful. It's about to actually show me how to get this problem. But the reason a lot of you wouldn't have written this down, and this is not a criticism, but the reason many of us wouldn't write this down is either we think we already know what the answer, so we just skip to the answer and like we move on with our lives. Turns out that answer might have been wrong. Or for some of us, we might even see that this problem is a little bit tricky or something. We might even see that we're not sure what the answer is, but the reason we wouldn't write all this down, or the reason we would suddenly invent in our mind, oh, I think I'll average the speeds, even though like we've never done that before. I never said the average speed equals the average of speeds, but the reason a lot of us might have just done that or not written this down is because unconsciously in the back of your mind, the reason a lot of people wouldn't want to write this down is because somewhere in their mind, they know, wait, I don't know the distance up. I don't know the distance down, right? I mean, please like stay with me here. I'm saying this is correct what I just wrote down, but a lot of you wouldn't write it down. Part of it, some of you might think the reason I wouldn't write it down is because it's so obvious and correct, like why do I bother? But the real reason a lot of you wouldn't write it down, and not only not write it down, but in fact shift gears and make up a whole new equation that we never said was valid, is because somewhere in the back of your mind, you're already anticipating that you think you won't know what to do with this when you write it down, because you're already thinking like, well, I don't know all those freaking pieces of information. So like, so that must be the wrong route. Like your brain, some of you have shut down on the right thing to do because you think it might be a dead end path because you're already thinking without thinking it. I don't know the distance up. I don't know the distance down. He never gave us that. I certainly don't know the time up. I certainly don't know the time down. So that's 4 pieces of information there that I freaking don't know. So before even writing down, I scrap it in my mind and I go off and I jump into this other lifeboat that I just made up, which is average speed. And I'm saying, don't do that. Rely on what you know. Write this down. Trust yourself. Write this down. And even though it looks like it's invoking 4 pieces of information that we totally don't have, note one thing first. First, note it's only the distance up, really. that we don't know. I mean, if we did know the distance up, if we knew how big this hill, nice. Yes, Mark, well said. That is points right there. That ain't no joke. Exactly. We make the truth and then we find the truth and then we make it relevant. We don't write down something relevant and then try to make it true. Like, please put that on my gravestone if we're going to talk about that. Like, I could teach you no better secret than that, really. And it is a secret because no one ever does it. But yes, well done, Mark. I think that was Mark. Yes. Oh, right. So even though it looks like I have 4 pieces of information that are totally inaccessible to me, I think to myself, no, wait a second. What it is that I don't know the distance of the hill. That's why I'm annoyed at this problem, or why all of a sudden I got shaky with this problem or something, because Yagerbaum never told me how high this hill is. How high is it? But if Yagerbaum had said, note this, and it's true, I didn't tell you how high the hill is. That is what makes the problem tricky. I didn't tell you how high the hill is. But if you really think about it, that's the only thing I didn't tell. If I told you how high the hill is, then you would know how low the hill, right? If I told you the distance up, well, that's automatically the distance down because this is a round trip. And furthermore, if I did tell you the distance up, you would know the time up because you know the speed up, right? Like we just did this with the warm-up exercise. For example, if I told you that the hill was 40 miles high, then you would know that the time up is 1 hour because on the way up, you're going 40 miles an hour, right? And similarly, you would know that the time down is 1.5 hours. Is 2/3 of an hour, 40 minutes, because you know the speed on the way down. So what I'm here to say is, okay, there is a piece of information we don't have. It's actually what's making the problem tricky. There's one piece of information we don't have, and that is how high the hill is. Okay, that does not mean we should make up a whole new equation. That means we should focus on that piece of information, right? Let's recognize, like, what we don't know is the height of the hill. Let's write enough down that focuses us and makes us realize we don't know the height of the hill. Let's now confront that reality. I say we have 2 options. I'm looking at the time. We have 10 minutes. All right. We don't know the height of the hill. We have 2 options now. One will, and bear with me, and I'm going to try to talk fast. I'm going to try to not answer questions. The first option might bother some of you until we get to the end of it and do option 2. And then I think you'll retroactively all feel okay with it. So just have faith for a minute. Option one is again, knowing that we don't have the height of the hill, but that's all we don't have. Option 1 is assume this is a legitimate problem. Assume, that is to say, that I didn't make a mistake in the question. I mean, sometimes I do, but assume that nature didn't make a mistake, that it's a legitimate question, and put another way, assume that there is an answer. Assume this is an actual solvable problem. Not all problems are. And if it's not solvable, that makes it like real scientific research where you actually don't know. That's a whole can of worms. But if you assume that this is a solvable problem, then the fact that you don't have the distance of the hill seems like a liability at first. It seems like a problem. I don't know the distance of the hill. But in fact, if this question has an answer at all, what it really means is that the answer must be independent of the size of the hill. If this question has an answer at all, if it is a solvable problem, which I submit that it is, then that means that whatever height of the hill there is, we're going to get the same answer to the question because the height of the hill wasn't given. Now, I'm going to say this too. You might even say, well, I don't really, I'm not sure of that. Well, put another way, test it. Like maybe we don't know if the question is solvable, but what I'm really getting at is if the question means what it sounds like it means, it should mean that no matter what distance we put in for the hill, we'll end up getting the same answer anyway. So what we certainly can do as experimental scientists is we could try out a couple of different numbers for the distance of the hill and see what happens. See, if we get the same answer, regardless of what, like if we try 3 different hill heights, and there's no reason not to just try, right? Like once we realize all I don't know is the height of the hill, then try some certain height, either to see if you're going to get the same answer no matter what height you try, or to see if there's some pattern that emerges, like all we're missing is the height of the hill. So try a height of the hill and just even see what method you would do to see if you get the logic of this problem with some example hill height that you put in. Now, how would you know? I'm saying, for starters, let's make up a hill height. That is actually scientific. It sounds not scientific, but it's totally scientific. It's called experimentation. It's called research. So I'm going to make up a height of the hill. And once I realize, I'm going to conjecture, I'm going to posit, I'm going to hypothesize, whatever you want to call it. I'm going to define a height of the hill. Now it's up to me. Maybe I'll find out that I can't get away with that, but I'm not going to find out unless I try. And if I'm going to try some height of the hill, if it's up to me to try, I might as well try a height that's convenient to work with. If I could try any number in the world, why would I try 186,000 miles? That seems crazy. Also, I don't even want to try, I could say, oh, the hill is 1 mile high, but that's kind of a hard number to work with if our rates are like 40 and 60. So what I'm going to do is I'm going to make up a number that's convenient. I'm going to conjecture or posit or hypothesize. And again, some of you might think, wait, this is like guesswork. This is not science. No, bear with me. It's experimentation. And I think we're going to see something here. I think it's totally valid. And also there's a better method, or a more general method you'll see if we get to the end of this in 9 minutes. So I'm going to literally say, let's assume for the sake of argument, let's conjecture, let's posit, let's hypothesize that the hill is 120 miles high. That's a very high hill. So what? I'm going to just try to see what happens, to see if I know how to solve this problem if I did have a height. If I did have a height. Again, remember, this problem is only hard because I don't know the height. So let's make it easier and see what I would do if I did have a height. So I say that the height of the hill is 120. Then the distance up is clearly 120. The distance, so now I'm filling in all the 4 facts that I needed, right? The distance down is 120. If I say that the hill is 120 miles, then the time up, look at my math at the bottom there, then the time up is 3 hours, right? 120 miles divided by 40 miles per hour. The units work out, the miles cancel, the hours flip up. Put another way, if average speed equals distance over time, then cross multiply and divide. I mean, I skipped a step here, do it on your notes if you're more comfortable, but time must equal time must equal distance divided by average speed. So if the hill is 120 miles, then the hill on the way up takes us 3 hours because we're going 40, right? And then on the way down, by the same logic, boom, on the way down, we went 60 miles an hour. So on the way down, we would take less time because we're going faster, right? It would take 2 hours to go down, right? This is all assuming that the height of the hill is 120 miles, which I know I just made up. But if I make up that number 120, what I find, and this is starting to look now like what I think it was Ruby who put in the chat. And again, forgive me, I'm going to go a little faster. I got 7 minutes. But I know I just made up 120. I just made up as a hypothesis. But if I make up 120, then what I get is 120 plus 120 in the top, 240 divided by 5 in the bottom, I get 48 miles per hour. Now, before I go any further, that doesn't prove anything. That's just like a step. But let me say that for starters, that 48 seems kind of reasonable to me. It doesn't seem crazy because on the one hand, it is somewhere between 40 and 60. Like it is faster than 40, but slower than 60, which you would expect an average to be. But it's a little closer to 40 than it is to 60. Now, why might that be? Oh, this starts to get at what like John and other people were putting in the chat. The reason my average speed is not 50, but possibly a number a little bit slower than 50 is because look what my math just showed. No matter what, I take more time to go up the hill than I do to come down the hill. I spend more time going 40 miles an hour than I do going 60 miles an hour. In fact, very specifically, if I spend 3 hours going 40 miles, if the hill's 120, then I spend 3 hours going 40 and I only spend 2 hours going 60. So even if you want to think in terms of averages, I'm not saying this bears, of course, the word average speed is called average for a reason. But if we're really going to think about averages here, it's not like taking 2 tests where you got a 60 on one test and you got a 40 on the other, and you average them together and say, my average is a 50. No, if you really start thinking about it, if our independent variable for motion is time, if you really think about it, it's like we spent 3 hours going 40 miles an hour. We only spent 2 hours going 60. So it's as though you were averaging tests. It's as though you got a 40 and a 40 and a 40, like 3 40s, and you got 2 60s on tests. Add all those up, divide by 5, and you would get your average is 48. In other words, if you want to think of this as an average, it's really a weighted average because we didn't spend the same amount of time going one distance as the other. Now, again, I only have 5 minutes. I'm saying the answer is 48. I'm saying that, but you might well be saying, all right, but everything you're saying out around is like, okay, but it all still assumes this made up 120 that you made up. But I made up the 120 to show myself something. I mean, look, let me go to the next page. Say I change my number and I try something else like 240, right? Then everything that's in the numerator of this fraction is going to double. Like instead of 120 plus 120, I'm going to have 240 plus 240. But everything in the new denominator is going to double accordingly too. Like it's the same ratios. I'm going to spend, instead of a ratio of 3 to 2 hours, I'm going to, going slower and faster, I'm going to spend 6 to 4 hours, because distance equals rate times time. Distance is directly proportional to time when the speed is constant, right? So everything in the top is going to double if I pick a different hill height, but everything in the bottom is going to double also. Because by making the hill height longer, I do make a greater distance, but I accordingly make more time that I have to spend on that distance. And I'm still going to find again that it's like 5, that again, I spend like 3 of my pieces of time going the slow speed and 2 of my pieces of time going the fast speed. So even if I try a different hill length, I'm going to get 48 again, right? And finally, then, even if you're like, really, I have to go through all this work to solve this stupid problem? Like, I have to try different numbers and see that, like, how was I supposed to know they'd be the same? All right, let's say you don't, just say this doesn't seem scientific to you. It seems like I'm making things up. Do the scientific thing. Realize I'm doing all this. I'm making up a number so that I can see what I would do if I did have that number. Because my only difficulty in this problem is I'm missing a number. Like, and if this were an exam, you might be like, I know what to do, but I'm missing a number. So just see what you would do if you did have that number, because then you'll see things in the process. In other words, what I could have done to skip all of this, if I really want to be scientific, I could have just said, I'm missing the next page, let's go. I could have said, I don't know the hill height. That's all I don't know. That's my problem in life. So call it X. Call it X. And now suddenly this is legitimate algebra, right? So then, So then I'm not making up anything. I'm just calling it X. And what do I find? Then my average speed would be X plus X all over X over 40 plus X over 60. And if I write it like that, then I see, you can factor out an X on the top, factor out an X on the bottom. You see the X's cancel out. When you put in X, what you see is literally the distance of the hill cancels out. It literally doesn't matter. It's proving my original conjecture that if the question was a legitimate question and there was an answer, the answer couldn't depend on the height of the hill. It doesn't. The height of the hill cancels out. And what you get at the end is simply 2 over 1 over 60 plus 1 over 40, right? And so that is pure math. Like, just get a common denominator for each. Like, I'm adding fractions, so I get a common denominator. Oh, surprise, surprise, my common denominator is 120. That's why I picked that from before. And so if you do this strictly algebraically, or strictly, you get the answer 48. And please notice, because I know classes is just about over, notice it took I don't know how many people got it right, how many people got it wrong, but my point is the correct answer to this question, 48. We did not invent any new methods to get it. We did not invent any new formula, new equation. We didn't pull any knowledge out of a black bag. We simply used the knowledge we had, which is average speed equals distance over time. If you got a wrong answer, oddly, it is because you made up something that isn't true. I mean, that's what seems unfair about this problem is it seems like we had to make up something new to do it. But no, it's the opposite. It's trust what you know. And if you actually trust the step process, then you find out something you didn't know before. The answer is 48. Okay, that's totally class. You guys have been very, very patient and very funny. And I hope everybody did. And that's all I wanted to teach today. So we did actually get through all the material. So yay. I apologize to those of you who thought we were wasting time with the jokes, but they do help me too. Bye. Thank you guys very much. And I also hope nobody was offended by like the haters and stuff. I hope this is all in the love it is to me. Thank you guys very much. So bye. I'm just going to hang out for 2 seconds if there's any questions. And other than that, I'm going to go teach my other class. But thank you. Yes, have a good rest of everything in the world. Thank you. Awesome. Yes, you too. Enjoy.
Bye, Professor. Have a good day.
You too. Thank you so much.